Hi guys, today we're going to be talking about bitwise operations, and this is for an upcoming stream. So the way this works is you're going to have this sort of like lecture type thing. It's just background on the topic, and then there's going to be some practice problems on it, and then there's going to be a stream afterwards that will take questions about the material, and it will also go over all the practice problems. So you can find the link to the practice problems in a Code Forces mashup in the description. And with that being said, let's get into the actual material. So, bitwise operations. The first thing is, what are bits? What is bitwise like at all? And so we're sort of going to start by deconstructing what like a binary number is. So if you don't know what that is, think first about decimal. Like say I write out this number, 137. When you look at this number, you sort of break it down into different pieces. Each digit means something different. In particular, this digit is the ones digit. This is the tens digit, and this is the hundreds digit. So in particular, this digit has a value of 10 to the 0, which is 1. This has a value of 10 to the 1, which is 10. This has a value of 10 to the 2, which is 100, and etc. In binary, it's a similar sort of thing, except instead of tens, we use 2s. So for example, 137 in binary, I believe would be this, 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 and this. See if I'm right. So essentially it's the same thing, except we only have ones and zeros because here we have tens, but each digit can go from 0 to 9. So this can represent the values from 0 times 10 to the 0 to 9 times 10 to the 0, which is 0 to 9. This represents 0 to 90, counting up by 10. This represents 0 to 900, etc. But in this, it's only ones and zeros. So we either get 0 or we get the power of 2. So everything follows from here. We get 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. It's a bit messy. 2 to the 5, 2 to the 6. I don't know why I picked such a big number, but yeah. So in short, this is 128, this is 8, this is 1, it comes to 137. So each digit represents 2 to the power of that digit. Now, there's something important here that let's take the sum of the values of all of these digits. As it turns out, it's equal to this. You can prove that this is the case for every number using like induction or something, but the point is the significance of this digit is always more than the significance of every other digit before it. And this is important when you're doing, for example, greedy. If you can take the higher bit, it doesn't matter what you can do with the lower bits. You always want to take the higher bit because the higher bit will give you more contribution than every other bit that's lower. That's one thing to keep in mind. So in terms of conversion, well, to convert from binary to decimal, you can simply sum the powers of 2s from the 1s. In this case, we did this here. And from decimal to binary, essentially you can start from the largest power of 2, and then you can go down and see which ones will actually fit into it. So like, for example, here we have 137. So we look at, for example, 2 to the 8th, which is 256, which is too high, so this is a 0. If we look at 2 to the 7th, it's 128, which does fit. So now we have a 1. Now we're left with 9. So 6 doesn't fit. 5 doesn't fit. I'll skip some stuff. 4 doesn't fit. 3 is 2 to the 3rd is 8. So that does fit. You get the point. That's how we convert to binary. Although your computer will essentially do this automatically. You'll be able to represent numbers in decimal as normal, and you'll also be able to represent them in binary. In code, if you wanted this number specifically, if you wanted 137 in binary, at least in C++, you can use something like the prefix 0b tells this that it's in binary. So you could have 0b 10001001. And that would tell it to be 137. So now that we've gone over how we tell the computer that we want to use binary, let's talk a bit about how binary is actually represented in computers. It's not necessarily the most important to know all of this, but it helps to know about the data types you're using and what their limitations are. So first things first, there's this concept of a signed number, and the sign just represents if something is positive or negative. So let's take, for example, an 8-bit integer, because 32-bit is too long to draw out. So for example, we'll have something like this. Now the way this works is the first bit is going to determine whether the number is positive or negative. It does this via a method called 2's complement, which I'm not going to describe here, but that's how it represents negative numbers. And then the rest of it, it's not the exact same as what you'd expect. It's a bit different. So you should look that up if you want to see how negative numbers are done. And then the rest of it is just directly the value. So an 8-bit integer can really only represent a positive value of up to, well, it goes from all zeros, which is 0, to all ones, which is 2 to the 6 minus 1. And then on the negative side, it can go up to negative 2 to the 6th. So really the whole range is negative 2 to the 6th to 2 to the 6 minus 1. For 32-bit, the range is negative 2 to the 31, and then 2 to the 31 minus 1. And for 64, it's this, but there's 63 instead. So those are some of the common representations. And yeah, the computer will represent these numbers using binary strings of different sizes. For example, a character is an 8-bit or 1 byte binary string. An int is 32 bits, which means it just uses 32 bits of information to store the value. And of course, it stores it in binary using this representation described above. And something like a long or a long in, for example, Java will store 64 bits. A long being C++. All right, now we're going to talk about the actual bitwise operations. Bitwise AND, OR, XOR, and NOT. And we're going to go over both their bitwise and their logical versions, and I'll explain what that means in a second. So bitwise AND, we'll start with that one, is essentially, it takes in 2 bits. So for example, 0, 0, 0, 1, 1, 0, 1, 1. These are all the possible inputs for the 2 different bits. This is usually called a truth table. Sometimes it's represented in different orders, but this is how it is. And then the output is, it takes in these 2 bits. It will return a 1 only if both of the input bits are 1. So the AND is kind of like a function. It's a function of 2 bits, and it will return 1 bit. So it will return 1 or true only if both inputs are 1, otherwise it returns 0. So what happens if you have more than 2 arguments? For example, sometimes you can have a whole array and you want to take the bitwise AND of all of them. Well, as it turns out, it will behave the same way. Only if all of them are 1 will the bitwise AND return 1. Otherwise, it returns 0. So if there is a single 0, the whole bitwise AND will come crashing down. It will become 0. So else implies any 0. So that is sort of the way bitwise AND works. Bitwise OR is similar, except it sort of behaves the opposite. Here's, for example, a truth table. It will essentially return 1 if there's at least 1 1, and it will return 0 only if everything is a 0. So if all are 0, then it returns 0, else it returns 1. So if we have any 1, then it will return 1. So it's similar behavior, but it's sort of the opposite. And then there's XOR. I don't have space. And I can't scroll because I don't know how OneNote works. Okay, so there's XOR. I guess I will compress the truth tables. So XOR will return, it essentially checks if the 2 bits are the same. If the 2 bits are the same, it will return 0. If the 2 bits are different, it will return 1. XOR has some very special properties that involve linear algebra, but I'm not going to go into that. Instead, I'll just say with many different arguments, it's essentially, it will return 0 if there's an even number of ones. Otherwise, there's an odd number of ones, and therefore it returns 1. This is true because imagine you start off with 0. When you XOR something with 1, it becomes its opposite. So if something is XORed with 1, it becomes its opposite. And if something is XORed with 0, then it becomes the same. This is something you can observe just by looking at the truth table. For example, everything that's XORed with 0, with y equals 0, this stays the same, this stays the same. And with 1, this becomes the opposite, this becomes the opposite. There's also bitwise not, which is very simple. It just takes in a single argument, and it returns the opposite. So it's just not whatever it is. Not is pretty simple. So note that all of these operations, suppose there are multi-bit numbers. For example, we could have 3 and 6. So in binary, these numbers are 0, 1, 1, and 1, 1, 0. So notice that these only took in 1 bit, which is kind of bad because, like, what are we going to do with that? Well, the way these operations work, and they're called bitwise for this reason, is because they do it like bitwise. They do one by one, they go bit by bit, sort of independently. So we'll take the bitwise AND of these 2 bits independently, the bit in the 2's position. Then it will take the bitwise AND of the 1's position independently, and then the 0's position. So we'll do this like this. This will become 0, this will become 1, this will become 0. And then we'll end up with 2. The other operations behave in the same way. Another and a bit more intuitive understanding of AND, similar to the XOR, is what happens when you when you AND with 0, you always get 0. Because no matter what, this 0 is going to bring you crashing down. It doesn't matter what the other argument is. And if you AND with 1, then it becomes the same. Because if the other argument was a 0, it'll be a 0. If the other argument was a 1, it'll be a 1. So OR, again, behaves sort of oppositely. So if you OR with 0, it'll become the same because the 0 doesn't affect anything. If you OR with 1, the 1 dominates and it becomes 1. So it's sort of different ways to think about it. Things like adding on some variable and seeing how it will affect it. For example, if you add on a 0 to the end, it will make it 0. So there's some different ways to like include them in problems. So this is how bitwise operators work. There are also logical operators, which you're probably more used to, and they operate with only 0s and 1s. They're sort of more like if conditions, stuff like that. If x and y. This is stuff like double and or double bar. And OR is represented with a bar, AND is represented with an AND. XOR is a caret, and not is a tilde. These are the bitwise versions. And then for logical, you have double and, double bar, and you have exclamation for not. So all of these treat variables like either 0s or 1s. But what if you have something that's not 1? Well, as it turns out, 1 in logical terms is anything not 0. So, for example, 2 logical and 3 will become 1 because both of these are not 0, so they're logically 1, and therefore they both evaluate to 1. That's how logical operators work. So that's sort of a brief thing. They're not that important. Well, actually, you'll use them for other things. But we're more focusing on like the bitwise operations. So an important detail about the bitwise operations is, as I mentioned, they treat bits independently. So if you're doing a problem and everything you're doing is a bitwise operation, then every bit is going to be independent of the other ones. And that means that you can sort of solve for each bit independently. And that way, instead of working with whole numbers, you're just working with inputs of 0s and 1s, and you're doing that for each bit independently, and then you'll put it all together at the end. This is an important problem-solving technique. A lot of problems use this technique. So pay attention to that. Try and think about it. So I'll give an example just to demonstrate how powerful that is already. So we're going to Yeah, we're gonna find, I'm asking you to find the number of pairs of A and B such that A and B are between 0 and 2 to the 60th. I guess you can say like mod something, it doesn't really matter. That and to a specific number. Jesus, I just dropped my phone. That and to a specific number. So I'll give you a moment to think about that. You can pause if you want. But the point is, we're going to use the fact that bits are independent. So really, because A and B are up to 2 to the 60th, it means that we don't have any restrictions on like essentially we're looking at numbers of length 60. We can have every number of length 60. So what I'm saying is we can treat bits independently because, like, say we had like 5, for example, then the bit we had in the 2's position would matter, because if we had a 1, then we can only do 1, 0, 0 or 1, 0, 1. But if we had a 0, we can do everything because it's small enough. But because we have 2 to the 60th minus 1, which is 1 minus the power of 2, we get every possible number of length 60. So we don't have to worry about like how big the number is. So that's one specific constraint. It sort of helps us that that's the constraint. So the other part is the other part is, so how do we actually count this? Well, now that we know that we don't really care about how large the numbers are, it means the bits are always completely independent of each other. So we can solve for each bit independently, we can put that answer together at the end, we're good. So let's look at a specific bit of k. If this bit is 0, then what's going to happen? Well, we can consider this bit in A and B. So for example, if it's 0 and 0, we get 0, which is what we want. If it's 0 and 1, 1 or 0, we get 0 for all of these. So 1 and 1 is the only case where it's bad. So really for this bit, there are 3 possibilities for what we can do. The respective bits in all of these places can be one of 3 options. So for every 0 we have in k, we get 3 options. And what about 1? Well, the only one that works is if we have all 1s, not all 0s. If we have all 1s, that's the only option. So we only have 1 option for 1s. So really, the answer is 3 to the number of 0s in k, because every 0 gives us 3 options and every 1 gives us only 1 option. And so that's how we do this. We isolate each bit, and then each bit has its own solution. They're independent, so we can sort of multiply them together. One final part is bit shifts. And bit shifts are sort of simple. Essentially what they do is they're just going to shift all of the bits by some specific number. So for example, say I had the binary string 00010, and the bit shifts are, this is a left shift, and this is right shift. So if I had this number, and then I left shift it by 2, then what I'm trying to do is I'm going to shift the entire number 2 positions to the left. So I'm going to shift this 1 over here, it will go 2 positions to the left. And therefore this new number will become 01000. If I now right shift this 3 positions or something, then this whole thing will become 00001. If something goes off the screen, it will not circle back, it will just go off. So if I shift this forward to the left, I'll just get 0. The 1 will just disappear. Yeah. So one convenient thing about this is that, for example, say I shift something by 1, then it will go from a position representing 2 to the x to a position representing 2 to the x plus 1. And therefore it sort of doubles. apart from the stuff that gets like truncated off when it goes out of the number, everything will double. So this leads to the cool idea of being able to get like a power of 2 easily. If I want 2 to the x, I will take the number 1 and I will shift it by x, because every single shift doubles the number, so doubling it x times will become 2 to the x. And similarly, if I right shift, let's say I have 1, 0, 1, and I right shift by 1, then this will become 1, 0. So this will become 5 and 2. And it turns out doing a single right shift is equivalent to floor division of x over 2. So doing a right shift k times is equivalent to a floor division of x over 2 to the k. Note the explicit use of floor division because we're working with integers here. And it will just, like similarly to how on the left the numbers just disappear, on the right the numbers disappear too. So it essentially truncates the remainder because every number that's too small will just disappear. So there's some stuff you can do with shifts, some ways to think about like all the bitwise operations, and these are what they do. Alright, so now we're going to go over a few of the built-in functions that can help with certain bitwise operations. So one of them is called __ built-in popcount. There's no normal popcount, since built-in generally means used by the compiler. The normal popcount exists, but it's in C++ 20, and most sites like Codeforces don't support that, so that will not work. But what this does is counts the number of 1 bits in x. So for example, this is something like if it's 1010110001, this will return 4 because there are 4 1 bits. Note that this explicitly expects an int. If you pass it like a long, it will downcast it to an int, which means it could potentially overflow. So to use the long specific version, you'd use built-in popcount LL, and that LL specifies long. So there are other functions that do sort of similar things. There is built-in CTZ, which counts trailing zeros. And what that means is, like, trailing zeros is the number of zeros before the first one. Note that this will crash for 0, or it's undefined behavior for 0, so don't do that. And built-in CLZ will count leading zeros. This will also crash for 0, so be careful with that. So this applies to both of them. And the reason that the reason that popcount is annoying and it will force you to convert to int is because these built-in operations sort of depend on that, or rather specifically counting leading zeros. Because suppose I have the number 1 and I want to count the leading zeros for it. Well, that entirely depends on the number of bits in the integer. For example, if it's 32-bit, there are 31 zeros before it. What if it's 64-bit? Then there are 63 zeros. So this entirely depends on the data size. And so all three of these functions will automatically convert to int, and then you have to specify LL by doing built-in CTZ LL or built-in CLZ LL for long. So that's just something to keep in mind. So as an example, just to test your, understanding, I don't really know. I just explained it. So I don't know why I'm doing this, but as an example, I will challenge you to just find the highest bit in a 64-bit integer. So you can either find its location in terms of the bitwise hierarchy or its value itself. So I will pause for a second. You can go ahead and try if you want. So the highest bit is essentially, you can determine it by using the amount of leading zeros. Because The highest bit is the first thing that's not a 0. So for example, say you know that there are going to be, say you know that it tells you that there are 4 leading zeros, which means that you're here, this is one position, and then the rest of it is whatever the rest of it is. In this case, this would be 59 because the whole thing has to sum to 64. But the point is, with the number of zeros, you know the number of zeros in the beginning before you get to a 1. And that 1 is what you're interested in, because it is the highest bit here. There's no higher bit, otherwise you would have gotten something that isn't a 0 beforehand. So CLZ will tell you the number of leading zeros. Specifically, it will tell you, if you take 63 minus that value, that will tell you the position, and then to get the actual value of that, you can just take 2 to the power of that number. The reason I chose 63 is because it's correct. You can determine it by like trial and error, basically. You look at a specific example and see how much you need to adjust by. And 63 turns out to be the right number, because this is the 59th bit, and notice that you would get 4 zeros before it, so 63 minus 4 is 59, that's what you want. So that's how you do this. There are similar problems that sort of involve uses of these functions in ways that aren't standard, or obvious at least. So before we continue with the main content, I'll go over like a couple tricks that you can do. So one is you can mod by any power of 2 quickly. So for example, if you want mod 2, the trick to do it is you take the bitwise and with 1. If you want mod 2 to the 5th which is 32, you take the bitwise and of 31. And the reason is for mod 2 to the x, all you're really interested in is the last x bits. So for example, for 2 to the 5th, 31 is like, in like an 8-bit integer, it would be 0001111. And so bitwise ANDing with it will, remember, ANDing anything with 0 becomes 0, anything with 1 becomes itself. So every bit except for the last 5 will be deleted because they'll become 0. So the 1s are the only things that matter, and they allow you to extract only that specific bit. And in general, this is usually very useful because using this bitwise AND, you can get any particular bit of a number. So this sort of, so mod 2 to the x, you could do bitwise AND of 2 to the x minus 1. And so talking about getting the particular bit of a number, now we can ask, how do we get a certain bit of a number? So for example, the kth bit of a number x. And one way to do that is we can use shifts. So for example, say we want 3rd bit of like 0, 0, 1, it doesn't really matter what the number is, but say we want the 3rd bit of this. So first what we can do is we can shift this 3 to the right. So that this becomes, well, it becomes this plus a bunch of zeros at the beginning. So this will be 0, 0, 0, and then it'll be this number, so it'll be 0, 0, 1, 0, 1. So this shifts 3 to the right, and therefore now the 3rd bit is now at position 0. So all we need to do is isolate the bit in position 0, and we know how to do that. We bitwise AND it with 1. So that everything else gets deleted, and so we only get this bit. And it'll be 0 or 1 depending on what the value of this bit was. So in general, if you want the kth bit of x, you can use the formula x right shifted by k, k, and then bitwise ANDed with 1. That's another trick you can do. There are also a couple of well-known identities. I'll go over one. This one in particular is this. No, sorry. A plus b is equal to a XOR b plus 2 times a bitwise AND b. And the reasoning is because of how addition works in general. So for example, say we're adding 2 numbers. I'll add 2 numbers like this, 0, 0, 0, 1, 1, 0, 1, 1. I will add these 2 numbers together. It happens to be a truth table. So for this, the contribution of these two digits is nothing because we're adding two zeros together. Here it's going to be 1 and 1, and here it's going to be 2. But we don't like 2's in binary, except for here, I guess. So the way this formula sort of works is if they're different, then it means we have 1, 0, and 1, 1. And so XOR works here because it means that this XOR will evaluate to 1. And then suppose they're the same, then we get 2 1s, and so this XOR evaluates to 0. So we need to compensate because 2 1s means 2, and that's where this 2 A and B comes in. This AND only activates when both of them are 1s, and so this will work for this pairing. It will add 2. Another thing you can do is, for example, A bitwise OR B plus A bitwise AND B. You can, again, verify it for the cases. This will OR to 1 and AND to 0. This will OR and AND to 0, and this will OR to 1 and AND to 1. So it'll become exactly what you want. Note that there is no 2 here because we don't need it anymore. This is just 1. And this is also 1. Yeah, there are other identities. I'm not going to go over that many of them, honestly, because I don't know that many of them. I'm sure you'll encounter them as you go along. You can probably also try and derive some of them. Alright, there's one main other thing I will cover in terms of what we can do with bitwise stuff, and that is we can represent a list of bits in just a single integer, because computers represent things in binary. So if we have some list of bits, like just some list of bits for whatever reason, like we have 8 variables that they need to keep track of, and they can all be zeros or ones, then we can instead represent it as like an 8-bit integer or something like that. If we have, for example, 32 or 64 zeros and ones that we need to maintain, we can represent that in an integer like that. Say we have like thousands. For example, say we have 6,400. We can use 100 integers to represent it, and then it's sort of easier to do that because, say, for example, we need to do some basic operations like bitwise and stuff like that. Like, for example, we need to get the bitwise and of all of these numbers sufficiently. Instead of taking each number and anding them sort of individually, we can use these groups of 64 bits. Like, we have 164-bit integers and all of them represent the list of zeros and ones. Then we can do that and we can bitwise AND them together instead. And then we're only doing 64 bitwise ANDs. Say we need to count the number of ones. I kind of forgot to mention the built-in functions, popcount, the other ones, etc., are also fast. They're not like as fast as basic bitwise operations, but they're pretty fast. They're better than doing things manually. So if we wanted to count, we could count each of these integers, and then the complexity is only 100 times O of count instead of the whole like 6,400 bits. We can simply do a single count for each of these numbers. And this is the main idea of bitsets. Bitsets basically represent these lists of bits using these numbers, and they chunk them into groups of 64 or 64 or 32 depending on your system, usually 32, and then they do it that way. And it's faster. Usually, for example, with 64, if you do an O of n operation, or reduce it to O of n over 64, because it's doing 1/64th of the work now. Everything, like the bitwise AND will do 64 operations at once. The pop count will do 64 operations at once every single time, so we only have to do 1/64th of them. And that's the idea of bitsets. So for example, if we have a problem like that's O of n cubed with n equals 2000, it would suffice to have something like O of 2000 cubed over 64 using something like a bitset. That would work. Yeah. And then the other part is using bitmask DP. So this is a thing where the DP state is essentially where the DP state is sort of like a bunch of zeros or ones. It's a similar thing to compressing a bunch of binary numbers into an integer. So for example, suppose we're like taking numbers from an array, and the state represents the set of numbers that we've taken. Instead of having something like DP of 6 different variables for each number, or like for each array value, that's stupid, right? Like, don't do this. This is absurd, right? So you have like 20 variables. That's going to be insane. You're going to have to write like a robot to auto-generate that code for you. It's going to be dumb. And it's going to be inefficient because you're making 20 array accesses each time. Instead, you can compress all these into a number. This can be, for example, a 6-bit number, or like an 8-bit number, or a 20 or 32-bit or 64. It doesn't really matter, but the point is these can be compressed into a number. And then we compress it all into a single bitmask. And this bitmask represents these 6 variables, but it's all inside a single number. And so that is the idea behind bitmask DP. There will be a few examples of this in the practice problems too. So another thing is an important identity that sort of works with bitmask DP. Suppose we're iterating over, we iterate from 0 to 2 to the n minus 1. And then, so like for example, suppose we're iterating over some mask. Then we're also going to iterate over all of the submasks of them. And a submask of like a bitmask is any mask that has that like all of the bits in the larger mask are set in the all of the bits in the submask are set in the larger mask as well, and potentially not some of them. But no bit is set in the submask that's not set in the larger mask. So basically the larger mask is like a superset, and the submask is like a subset if you consider the ones as stuff like that. So if we iterate over all submasks, it's going to be 2 to the pop count. It's going to be 2 to the number of ones, because each one in the larger mask can be 0 or 1 in the submask. And it turns out the sum from I equals 0, the total cost of iterating over these submasks of 2 to the pop count of I is equal to 3 to the n, which is the total complexity that we'll get of iterating over all submasks of some specific number. And the reasoning is that like with a bit, with like a binary number, every number can be either 0 or 1. With sort of this formulation of iterating over submasks, every number has 3 possible states. So for example, consider this. This is 0 in both. This number is 0 in both. This is 1 in the larger mask, but it's not 1 in the submask. So we can label this, for example, 1. This is 1 in both, so we can label it with 2. This is 0, this is 2, this is 0, this is 2. So each number has one of 3 possible states. It can be 0 in both, it can be 1 in the larger mask but not the submask, and it can be 1 in both. So because of this, each number has 3 possibilities, so there are 3 to the n possibilities of each one. So that's the total complexity of iterating over all submasks of every number. This is something we could commonly do in bitmask DP. Sometimes the transition requires doing that. Yeah, that's about it. I haven't really explained exactly how bitmask DP works, but it's essentially just using a set of numbers taken as a DP state. If you don't understand DP, it wouldn't make sense. It wouldn't make that much sense to you. And I'll also again go over some examples so it'll become more clear from the mashup. Or you could try to figure it out yourself, or like try to formulate it yourself with the practice problems. So that may have been a lot to take in like at once, but I'll basically come out with like the two main takeaways. One is the greedy idea that I presented before, that 2 to the x is greater than 2 to the x minus 1 plus 2 to the x minus 2, etc., up to 2 to the 0, which is equal to overall 2 to the x, that minus 1. And so when you are doing greedy with, like, for example, you're doing greedy to make the largest number possible, taking the higher bit is always going to be worth it over taking any of the lower bits. So if you have a choice to take the higher bit, but it may like make the answer worse for the lower bits, do it, because the higher bit is always going to be more influential than the other ones. And the other is that bitwise operations treat bits independently. Remember that bitwise any two numbers will do the numbers independently. Like it'll do each position independent of the other positions. So this will become 0, 1, and 0 just because each bit independently. So if you have a bunch of bitwise operations and that's all that's going on, you can treat each bit as its own independent entity. You can solve the problem for that bit position, and then you can combine them all at the end. If you're counting something, for example, you combine them by multiplying. You could do something like that. You'll see a couple practice problems with that idea as well, so be aware of it. And yeah, just a couple notes. I'm not going to be doing this stream in this dorm, and one reason is because this place really sucks. I don't know if you see me sweating through this whole thing, but I had to turn my fan off because it totally messes up my audio. And God, it's like the heat is crippling my mind. I'm gonna have to heavily edit this video to cut out all the times I just pause because my train of thought goes like out the window. So yeah, I'm gonna make my best effort to do as much at home as I can instead of here, because there's no AC and it's not great here. But yeah, so that's one thing. You won't see that much in college, but later on as the weather settles down, I'll do more videos here. I guess that's what I'm trying to get at. I'll put some resources in the description. I'll put the practice problems in the description in the form of a mashup. Just like check the description. You'll find a bunch of stuff there. I believe that's it. Goodbye.